So now we are going to work on improper integrals. And this first one actually isn't improper. This one is, again, one more little bit of review. This is just a definite integral because it has bounds of integration. So we're just going to make sure we remember how to do that. So remember, when we're doing a definite integral, the first thing we're going to do is integrate. So some of you might find it much easier to rewrite this problem as x to the negative 2 dx, because now it's just a basic power rule. So the power rule says we add 1 to the exponent and then divide by that number. So there we are. And then we still have our bounds of integration. So now we could rewrite this just slightly if we wanted to. You can make this as negative x to the negative 1 over the bounds of 1 to 5. So now we go ahead and substitute in our numbers. So this would be 5 to the negative 1 minus, let's see, a negative 1 to the negative 1. And just go ahead and simplify as much as you can. You say, okay, well, this would be negative 1 over 5 minus a negative, well, 1 to the negative 1 is just, again, it's just 1. So it ends up being plus 1. So therefore, 1 plus a negative 1/5 would make 4/5. So there would be our answer. So we could then also say that this converges to that value. And just as a quick reminder, we can also do this in our calculator. We can bring up the calculator, ignore that, and we're going to go ahead and type in our graph that we're integrating over. So it's x to the negative 2. And now we could go ahead and graph it. And we wait a half hour because the calculators are slow. Okay, there we go. And now we're going to go calculate. And option number 7 for integration. And our bounds of integration, the lower bound would be 1. The upper bound would be 5. And there we go. So our answer is 0.8, which is the same thing here as 4/5 would be 0.8. Perfect. Okay, now here's our first improper. All right, now to do improper integral, what you might notice is it kind of looks like a definite integral. We have bounds of integration, except one of our bounds is something where we cannot substitute it in. I can't substitute in infinity, just like we were talking about in the warm-up. You can't plug in infinity. So we're going to do something that seems absolutely silly, but it's really math geeky. But what we're going to do is make it so we're not substituting in infinity. We're going to substitute in a constant. So what I'm going to do is just say, we're going to change this into a limit. And now I'm going to use the letter k. You can really use any letter you want. It's just a letter. Okay. So I'm going to change this to the limit as k approaches infinity of the integral of 1 to k of 1 over x squared dx. So stop and pause and say, what did I really change? Well, everywhere I had an infinity, I wrote k, and now I just have a limit. So now here comes the really exciting part of the problem that I know you're all anxiously waiting to hear. Do the problem like normal. So what we're going to do is notice this is the same problem as the one we just did. Nothing has changed other than our bounds of integration. So if you want to, again, you can rewrite this as x to the negative 2. So now when we do this, oops, let me change colors on this. So now when we do this, this is going to be, x to the negative 1 over the bounds from 1 to k. So now when we go ahead and substitute that in, this would be what? The limit as k approaches infinity of k to the negative 1. Oops, excuse me, I forgot to divide by my negative 1. Excuse me. So therefore that'd be negative k to the negative k to the negative 1. Much better. Okay, minus a negative 1 to the negative 1. Okay, and you'll notice I didn't write the limit for the second part here because the second part doesn't have any k's in it. So I only need to do the limit of the first term. The second term, no k's, no limit needed. Okay, so here we go. So now we're almost done. Here we go. So we're going to say, if you want to, we'll do one more rewrite. This is k approaching infinity of negative 1 over k minus, well, plus, because a negative and negative make a positive, plus 1. So now what's going to happen here, is hopefully you're going to notice when we evaluate this limit, this is like the problems we did from the warm-up. This is going to be -1 over something big plus 1. And as we talked about before, 1 over something big makes 0, makes something really, really little. So therefore, the answer to this problem is 1. And does this problem converge or diverge? Well, it converges because it approaches a number. Okay, so there we go. There is your first improper integral. And what is the punchline to improper integrals? Well, whenever you're approaching a number, you can't just substitute in. You have to write it as a limit. Whenever we're approaching infinity, or maybe like a 0, if we were dividing by 0 in this problem, we'd have to just do a limit of the problem. And you just throw a constant in there, and then at the very end, you just approach it like you're doing a limit problem, and you've got your answer. Okay, so that's it. That's the big concept to this whole lesson. So I would highly recommend stop, pause, practice if you feel comfortable, and try to do as many of them as you can on your own. If not, watch the video, keep going. Okay, so for this next one, once again, we are approaching infinity, which means this is improper, which means I need to write this as a limit as k approaches infinity of 1 to k of e to the negative x dx. Now, for this problem, you might notice we need to use a little bit of substitution technique. Oh, fine, use u sub, no big deal. U equals negative x, so therefore du equals negative dx. And so if you want to rewrite that, you would say dx is equal to negative du. Now, there is a little bit of math geekiness here that to make it absolutely 100% mathematically correct, okay, we're gonna have to do something that's called suppressing your limits. Okay, what I'm going to do is suppressing our bounds. I'm going to go ahead and not write them, because the issue here is this is an x value. We're saying x is 1 and x is k. And I've now switched to u's because of my u sub. So therefore, I can't write those bounds there anymore. Now, after the problem, I will go back and show you how to write those bounds, and it's actually kind of nice. It makes it really easy. But so for now, let's just leave it like this. We're going to suppress them. So what we're going to do here is now just integrate. We've got our, all right. And if you want to, you might want to say, I want to pull that negative to the outside of the integral. I would highly recommend it. So there we go. So now the integration, not too bad. We're just going to say the integral of e to the u is e to the u. So we have the limit of k approaching infinity of negative e to the u. And now we switch back. Right now is where we say, okay, we're done with our integration, so we're going to switch back to x's. So we're going to have k approaching infinity of negative e to the negative x, going from the bounds of 1 to k. And went into a little Christmas mode there. Green, red, green. All right, let's not go back to red. So now we're going to go ahead and substitute in our values. So this is going to be k approaching infinity of negative k to the negative x. Try that one more time. Negative e to the negative k. That looks a lot better. Minus a negative e to the negative 1. And now, so for evaluating this, it's not too bad. Or if you want to, we can rewrite it as k approaching infinity of negative 1 over e to the k, so we don't have that negative exponent, minus a negative makes a positive, of 1 over e. Okay. So now, evaluating my limit, this would be negative 1 over e to the big plus 1 over e. And as we did in the warm-up and as we know now, e to the big is big. And negative 1 over big makes 0. So therefore my answer is 1 over e. And therefore this converges. Okay? Now, that would be enough. That would be enough using the suppressing your bounds concept. But to make it a little more math appropriate and make math teachers happy all around the world. Ooh, I'm going to have to go ahead and make some space there. To go ahead and make math teachers happy all around the world, because they're not going to like suppressing your limits, because they're going to be concerned, or suppressing your bounds, because they're going to be concerned you're going to forget them. You're going to forget that this thing was bounded, and you're going to stop somewhere in the middle of the problem. So what they've said is, look, it's super easy to convert. All you're going to do is take your bound, take your x values. We have an equation right here that changes x's into u's. So what we can do is just say substitute in 1. So right into there, plug in 1. So therefore I know u would be equal to -1. And then now substitute in k. So instead of k, this would be -k. There we go. So now, watch this. This is the even more magical portion of this. If I go ahead and do that, I don't have to substitute back in for x's, because I have these are u values now. Since I went ahead and substituted them in, all this extra work, all these extra steps, totally not needed. Now what I can do is just go right on to my next step and say, okay, I have these in terms of u's, so I don't have to substitute back into x. So let's just go ahead and substitute in. Let's substitute in. This is -e to the -k. That k just does not want to work. Minus a -e to the -1. That might look familiar. Looks somewhat similar. So now this is going to end up being -1 over e to the big, for the exact same reasons we did before, minus a positive 1 over e. And look at that. It's amazing. It ends up being 1 over e. So there you go. So what I will do from now on is every time we have to use a u sub, I am not going to go ahead and substitute back in my u's to change them back into x's. No, no, no. Instead, I'll change my bounds. I'll change my bounds from x values into u values, and then I never have to switch back. But again, that's only used for u sub. So if you have any problems that use u substitution, that's your way around it, or a way to make it a little easier, a little shorter. Okay, so problem number 4. Problem number 4. This problem, once again, this dreaded improper integral. It's an infinity. So what are we going to do? We're going to go ahead and write a limit as k approaches infinity. 1 over k to 1 over x dx. I know this is amazing. So now we have to go ahead and do our integration like normal. And 1 over x, hey, do we all remember that's our favorite one, because that's the hidden one. That's just natural log. And we're going to go ahead and say that's natural log evaluated from 1 to k. So now what we're going to get is the limit, the limit as k approaches infinity of the natural log of k minus the natural log of 1. So, oops, this is left over from the last problem. There we go. So now the fun part, the limit. Well, actually, we don't need the limit anymore, because I'm going to go ahead and substitute in the natural log of something really, really big minus the natural log of 1. Well, the natural log of 1, that's just 0. Okay, so that wasn't too bad. So now, what's the natural log of something big? Well, if you don't remember, you could go ahead and start typing in numbers into your calculator and saying, okay, natural log of something big is, man, that's 11. The natural log of something even bigger, got bigger. The natural log of something even bigger, and you can get the idea here. It got even bigger. Or if you want to, you could always go to the graph and kind of look at that and say the natural log of x. And you could use a table if you wanted to and let it spit out values for you. Or you can go ahead and look at the graph, and you'll see it's just increasing. It gets bigger and bigger and bigger, which means this approaches infinity, which means our whole thing approaches infinity, which means it diverges. So that's going to end up being relatively important later. Just the idea of saying, do we approach a value or do we not approach a value? And this one we're going to say we don't approach a value. It becomes infinite, and that might be important in the business world if this function is somehow related to costs, where we're saying the cost will just increase forever and ever and ever and ever. And ever. Or again, profits. That would be a good thing, where instead, if this was profits in the previous problem, if it was profits and they were approaching a number, well, then at some point you stop because you say this is the best we're ever going to do. Yes, we're going to go up marginally. We're going to approach this value, but we're only going to be making pennies. Who cares? Where if this was costs, then you would say let's just produce forever because it stops going up. Our values are approaching a number. So anyway, that's where I believe your business classes will take you with it. So nonetheless, just there's your ideas. Okay, so now I'm going to go ahead and take a little break and pick up in the next video.